Good afternoon, I'm here. Sorry about yesterday. I hope you made up for lost time and you worked on the next units, whatever was in the videos. I mean, the videos are complete. The ones that I have in the playlist for the live streams from last semester, you could just watch all of those along with the notes and get all the coverage of the course. All I feel that's missing is a nice treatment of regression. That's the only thing I didn't do. In the live streams. I left that with the students. And so I'm gonna complete Unit 3 today. I don't know if it's gonna take longer than 3 hours, but I'm gonna stay on and do it, or it might take less. I want to do the whole of Unit 3, regression. Maybe I should first ask if you have any questions. If you follow the notes, read the notes, and then go to the videos, or if you do it simultaneously, that's your best bet to understanding what I expect from you. In terms of grading your tests, I'm just waiting to get those from the grader, and that should be today. So while we're doing this, I'll see about getting those back to you. All right. And my impression was they were done fairly well. All right, so if you notice in regression, this is the first note I make to you, is that pages 13 to 18 are included for completeness. However, the material covered in these pages is really not what you need for this course. Like, it goes beyond the scope of the course. It's really good though for completeness to have that. If you're in economics, if you're going to be taking the economics class, that will be relevant, and you'll see that kind of stuff regarding transformations and interpretations of transformations. That's going to be covered in your economics class, but it's a nice introduction, and was actually a summary in these notes. All right, so what I then do is ask you to refer to the discussion about scatter plots way back in Unit 2 GDS, right at the end. I provide an example. How many of you saw that video of scatter plots? So that would be it's not the live stream videos, it's just in the regular videos. Let me tell you which one that one is. I'm going to tell you. Which it is. In StatsLongobardi playlist. So scatter plots is a video. Oh, I have several. 17, 18, and 19. Because I tried to keep them down to 5 minutes. 17, 18, and 19. Okay, so I'm going to put that in the chat. So this is in the playlist just StatsLongobardi playlist, not the live one. Watch V, no, I gotta remember what I said, V 17 to 19? 17 to 19. Okay, so I don't have a shortage of material. I recommend you watch all those videos, and I really want to reserve our meetings for just review, so I answer your questions. So, but I do feel like I should give this a nice full treatment. So in that video, what we talked about, I'm going to go I'm going to look at that document. So how many of you watched it? Can you tell me if you watched it already? So none of you watched it? These 3 videos? You guys can hear me, right? So in those 3 videos I describe, I explain scatter plots. No one? Okay, you guys got to catch up on your videos. So this is not going to be a course that's delivered by me. I hope that's already clear. It's already available. It's already laid out in the platform, and you have all the videos on YouTube. So how do we interpret scatter plots? So scatter plots are how we look at 2 variables at a time. How we look at 2 variables at a time. All right? And what we want to do is, again, just like for 1 variable, we need to first illustrate the data that we get. So let's say we have a sample. With that sample, we create a scatter plot. Scatter plot where you put, as usual, a variable on this axis and the other one here. Now, which one you put in either place matters when you want to make predictions from one to another. But if you just want to know the correlation, if you want to compute a statistic of correlation, it doesn't matter which one you put in each place. Okay? But you need to know what you want out of it. You need to, and you can always redraw it or recast it. So you'll plot the data as pairs in these XY coordinate axis. And then you'll comment on the overall pattern for regularities and curiosities. So anything that stands out away from the general pattern are what you would find interesting and maybe investigate. If some of the observations, I just turned it off, sorry. If some of the observations stray from the general pattern, maybe there was a key error, right? So this should sound familiar. Maybe somebody entered it wrong, so maybe somebody measured it wrong. So you could catch that once you see the general pattern and deviations from the general pattern. Then you want to comment on the form of the pattern. In particular, when we talk about regression or linear regression, we're looking for a linear pattern. So you would describe the overall pattern, its form, if it's linear or not, or there's just no pattern. The strength of that linear form and the direction of the linear form. the pattern appears reasonably linear, then we can use tools developed in statistics courses to calculate what's called the correlation coefficient. So this is the measure that captures the direction and strength of a linear relationship. So you only use that when you see a linear relationship. If you don't see a linear relationship and you see some other type of relationship, you calculate a different statistic. And R can be used for predictions, and I'll explain what that's all about. Also, you want to comment if the relationship is curved or clustered. That's what I'll describe below. Curve would be like okay, so this is from page 30 of the notes, I believe. In GDS. So this is the video you should have watched, and if you want, you can watch it. Maybe I say different things, but I'm not sure. I'll probably cover most of it here. So this is a curve relationship. If I was to fit a curve to it, a smooth curve, you can see that there. So this is a relationship, but it's called a non-linear relationship. If you can read that. All right. If you calculate the R for this, it's the wrong measure. In fact, the R of this, and I'll show you what R is if you don't know, the R of this turns out to be 0. And I'll explain why later. You could also have clustered data. Clustered data looks like that. So what you see is that the observations as a whole have, so I look at it and I think, could I fit a line to those? Like all of them? Maybe. And if a line is defined by the line that fits closest to all the points, then the line would have to be somewhere in the middle of all these clusters, somewhere like there. Okay? But they're really scattered around that line. If I split up the clusters, however, I see two distinct lines. And these lines actually go in the opposite direction as one that would go through all of them. So the question is, which lines, this one or these two, define the relationship? Before I answer that, how can this happen? How can you imagine this happening? There's a characteristic that splits the data that's not represented in X and Y. So let me give an example. The example that I have in the notes This is in the annotated notes. So on this axis, I have the number of hours of soap operas that were watched. Okay? And on this axis, I'm going to have a measure of, like, we conducted a survey with people who watch soap operas, and we also asked them questions about their general sense of well-being. So this is a measure of well-being or happy, you know, how happy they are. But I'll write well-being. A general sense of well-being. So what's happening is as hours increases, as hours are going up, overall, it looks like well-being is going up. Maybe that's too much of a slope. Maybe I'll make it more like this. So it has to fall like in the middle. Okay. So kind of as hours are going up, hours of watching soap operas are going up, well-being is going up. How am I looking at that? I'm dividing the data in half, like if through the middle. I'll explain better on the graphs below. But see, this is kind of in the middle of this information, and this is in the middle of this, and it's going up. But that's not exactly the relationship that stands out at us when we see the graph. This is the importance of making a graph. What I see is one group here and one group here, and it's the opposite. So what's going on? We would have to explore who these people are in this group and who these people are in this group. These are people who are watching more soap operas. Like the first person watches more than all these other people, and all the rest watch more hours than all these other people. Who's more likely to watch soap operas? Who's more likely to watch soap operas? That's the question. Because they're defined by this characteristic of watching soap operas. They aren't, in this axis, notice their range of well-being is about the same. These ones are a little bit lower. Their sense of well-being is about the same, just a little bit, like they can reach higher highs. Is it possible that these are just women and these are just men? That's the question. That characteristic is nowhere on this scatter plot. So we would have to investigate and see there's a third variable that's splitting up the behavior, and we see that now we see that for men, the more soap operas they watch, the lower their sense of well-being. And for women, if this is true, the more soap opera they watch, the lower their well-being. All right? And why would that happen? Well, is it that soap operas, are novelas making them less happy, or having it causes them to have a lesser sense of well-being? That could be. Seeing all these rich people on television might make them feel, wanting, envious. That could be it when they look at their lives. Or it's probably more likely, maybe that's part of it, but it's probably more likely that people who watch so much soap opera, they might be unemployed, they might be alone, they have no one to distract them, they might be, these factors contribute to well-being, right? They're negative predictors of well-being. You're going to be less happy because you're unemployed. You're less happy because you're alone. Or maybe you're disabled. So if you're disabled, you're less likely to be happy. So what I'm saying is, it's not that novellas are causing people to be more disappointed. It's just that there's a correlation. So there's a correlation that we want to measure. It's not causation. All right, so we did see that in the videos. Correlation is not causation. I don't know if you can hear my fan. I hope it's not too loud. So what we'd have to do in this case is we would have to do exactly that. Separate the data and find the correlation here and find the correlation here separately. And then also identify, well, depending what we want to do, make predictions and so on, which we're going to learn about, you'd actually compute the best line that fits through that data. All right. So I can ask you to, have a scatter plot, comment on the form, the strength, and the direction. So in this one, the form was nonlinear, so we don't answer the other questions. Here, the form was linear. Is this relationship, what is the direction of this relationship? Positive or negative? What is the direction of this relationship? Positive or negative? No comments? Okay, I'm going to teach that and you're going to answer next time. And what is the other question is the strength. All right, so let me show you below and then we'll go back. So the correlation is a measure of the direction and strength of the linear relationship between two quantitative variables. If you're analyzing two quantitative variables, but they're not linear, do not calculate the correlation coefficient. If you have two quantitative variables and they are linear, you can compute the well, you should graph first, for the reasons I explained above, to identify the linear relationship. And then you could compute the R, and the R will tell you, a single value will tell you the direction and the strength. So, for instance, R is between -1 to 1. We're going to talk about its calculation shortly. If the observations turn out to look like this, The R for this is positive 1. Now, how would we see that in without making any calculation? If the points fall perfectly on a line, the relationship is perfectly 1. It's either 1 or negative 1. If the relationship is such that it's going up, it's upsloping, it's all positive 1. But let me explain a little bit more about how to see that from the graph. I'm going to divide the data in 2 halves. So that's cutting it in half at the mean, if you can see that. And then I'm going to cut it in half at this mean, in this axis. Now we interpret up. What I've done is divided the data into 2 parts. We're not looking at 6 data points individually. I'm going to look at them as a group. And we say, when x is high, so when x is high above its mean, where is y? So when x is in this side above its mean, where is y relative to its mean? So remember, statistics is about averages and relative measures. Averages, I'm using the averages as the relative measure, and I'm comparing everything back to it. So when the value of x is above the mean, where is the value of y? Above or below? So when x is high, not x bar, but x. Y is high. So when x is high above its mean, y is high above its mean. These values are all in this upper quadrant here, x high, y high. When x is below its mean, where is y? So when x is low, y is low. You see? It's not up here, it's down here. So when x is low, y is low. So what you have is reinforcing variables. X high, y high. They reinforce each other. When x is low, y is low. When they do it perfectly, so x is here, y is just as much above its mean. So this is just as much, it's like, I can make a square here pretty much. It's perfect. So, and that, because it's perfect because it happens every time. All right? So that's what creates a positive relationship. Again, I'm going to show you how to calculate R so you can see that. What about a negative relationship? Let's look. I don't want to do it there. I'm going to do it below. Here we have a negative relationship. It's perfect and negative. So the direction is negative. The sign is, sorry, the direction is negative, so the sign is negative. And it's perfect, which makes it -1. So let's analyze it like we did the last one. Divide it in half using the mean in both directions. Okay? So, when x is high, y is where? High or low? When x is high above its mean, y is where in relation to the mean? Is it here or is it here? The observations are all where x is high, y is low. When x is low, y, so when we're here below the x bar, y is above its y bar. Those are opposites. Okay, so the pattern is has a negative trend. They're the opposite, and they're perfectly offsetting each other. They fall exactly on a line, so that's why I know the relationship is perfect. So the most perfect it can be is a -1 in the negative direction, because r will always be between 1 and -1. Very good. Okay, let's do some other ones now. What if, I'm going to draw 2 more. Okay, so what would be the r in each of these? Give me an idea. Well, take a guess at what r would be in the top one. What sign would it have? it would be a positive because I can see it's going up. But is it 1? It's not 1, right? It's not 1, but it's high. So it's going to be 0.8. Let's say, I just made up that number, but it's something higher, right? Maybe even 8.5. But I'm just going to leave it 0.8 because that's what I have in the notes. So that's that one. What about this one? It's very scattered, but there's kind of a slope here, kind of like down there, right? Like right in the middle. So it's going down, so it's a negative, but it's not as close to 1 as the one above. It's probably closer to 0. So I'll just say it's negative 0.5. Something like that. Okay, I'm not going to be precise about it. We're going to learn how to calculate it. You still don't even know the formula. I'm just giving you an idea. And then there's 2 more relationships I want to show you. If the data is like this, or the data is like this, neither of these are linear. So you should not calculate the R for either of these. If you did, what would you get? Let's divide it in half. So let's say this is halfway, and this one is halfway. Let's do one at a time. So we see in this case when x is high, I don't know, looks like my video froze. I'm gonna have to reboot this. I think my video froze. Yeah, my video froze a little bit back. I don't know. I'm gonna have to reboot. Stay there. I don't know what to do. Let's. I don't know how to kick it to get started again. What happened? Why did it do that to me? Same video. Why is it giving me the same video? Why is it so frozen? So I have to restart. Ah, there we go. We're back. I think we're back. Okay. All right, so if it cuts out again, just text me, because I might not see it in the chat. Just text me. You know my number, right? I'm going to put it here. Text me if you see some. Please write my number down so I don't have to put it up here every time. All right, good. All right, so when we're looking here, you have, okay, so I've divided the data in half this direction and with this variable. And now we look, do the same analysis. When x is high, above its mean, in other words, so again, we split the data in half, high and low. When x is high, what is y? X is high and y is in both places. Y is both above its mean and below its mean when x is high. There's data here and here. So it's indeterminate. There's not a pattern. So the y is like mixed between high and low. And when x is low, so it's below its mean here, y is in both places again. Okay, so that is going to create no trend. There's going to be no trend here. This is not a linear relationship. There's actually no relationship here. There's no relationship. It's not linear, it's not non-linear, there's no curve, nothing. And it turns out in this case that r will be 0. Again, I'm going to show you why when we do the next bit. What about below? In the curved drawing, let's do the same thing. I'm going to divide up the data in half. That cuts through at x bar, and this kind of cuts through at y bar. Same thing, you see? When x is high, y is in both places. When x is low, y is in both places. Same result. Also, r will be equal to 0. But you should not compute it here. Okay, because it's a curved relationship. This is called a non-linear or curved relationship. Okay. Okay. So watch all those videos to review that. You can skip over anything because I just did this part, but watch videos 17 to 19 in the regular playlist to see what else I have to say about that. I just wanted to give you that run through so that now I can go into and then go back to the notes. So in the notes, remembering, just loading it. So page 13 or 18 are not required reading, and the rest are just exercises. So this is actually a very short unit. This is the shortest unit. So what is the sample correlation coefficient? I've been talking about it without even showing you how it's computed. It is a statistic since it is a number calculated from the sample of pairs of data, pairs of observations. It measures the direction as seen as its sign, and the strength as seen as its magnitude between -1 and 1. And it does this for a linear relationship between two quantitative variables. You cannot calculate R if you shouldn't report R for a nonlinear relationship or no relationship that's linear, and you shouldn't calculate it when the variables are anything but quantitative. How is it computed? Here's the formula. So what is this? What do you recognize here in this formula? Tell me a few things that you recognize. What do you see here that you recognize? Nobody? Well, I see the sample mean of X and of Y. And I see the sample standard deviation of X and of Y, and I see this. This is an average. Remember what we discussed about average. When I see sigma and an N on the bottom, I should think average. It's an average of the multiple here. It's N minus 1 because I'm using estimates of a pair inside of an estimator. So there's 1 degree of freedom that I lose because I'm using 1 point to estimate R. If you saw the video for calculating standard deviation, I discussed reducing N by 1 degree of freedom. So now what's this? Anyone? 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 So if I was to write this in Greek letters, this would be and what's that? This essentially is standardizing the values of x, converting each observation to its standard deviations from its mean. And it's converting the y, its pair, from y, its observed value, to the number of standard deviations from its mean. Okay, so we're converting it into a standardized number. This is what forces r in between to be between -1 and 1. We're going to make some calculations with that too in a bit. Okay, so this is standardized. These are both standardized. And then I average that after multiplying them. So what you'll see, when x is high, what will this be? Positive or negative? High means x is above its mean. So this would be a positive. So x high this will be a positive. If y is also high, when x is high, if that is the tendency of the pattern, like what we saw just now, so when x is high, y is high, so let's say it was like that. Okay, so when x is high, here, y tends to be, oh, I made it mixed up, didn't I? I gotta do that again. I need to get rid of this thing. There. Okay, so I'm going to cut the data in half. That would be here, and this data in half there. So when x is high, I'll make some more points. You guys get the point, right? All right, so when in this scatter plot that's always up here, when x is high above its mean, so when x is here, y is here. So in this case, x high, y high means this will be positive and this will be positive. That will contribute a positive value to this calculation. Okay, to this, it'll contribute a positive value. What if when x is low, below its mean, y is mostly low below its mean? That'll contribute what? So when x is low, y is low. When x is low, this will be a low number minus a value higher than it, right? Because x is low. This will be a negative. This will always be a positive. This will be a negative. And when when y is low, the standardized value will be also a negative. A negative times a negative also contributes a positive. So you see the formula mimics the pattern I'm showing you, okay? So it's going to capture this behavior when x is high, y is high. If that's the case, then you're going to be contributing positives. If it's also the case that x is low, y is low, because of the way this is calculated, you will always contribute positive values. If the relationship is down-sloping negative, so let's say it's not picking up my dots. Okay. Here's just the axis. In this case, we see kind of a negative relationship. It's quite scattered, but it's going down. As x goes up, y seems to go down. If I split up the data in half this way and half this way, mostly when x is high, y is low down here. When x is low, y is mostly up here. What will that do? What will that accomplish? Well, if I'm going too slow, you guys can speed me up in the replay. You can speed up my voice. Okay, so when x is low, when x is high, y tends to be low, so that this one will be a positive, but this one will be a negative. That'll contribute then, because a positive times a negative is going to be a negative. So it'll contribute negative values. And similarly, if we do it the other way around, when x is low, y tends to be up here. So that also contributes a negative, because they're opposites in the calculation. So when x is low, this value will be a low number, making this a negative, but this one will be high, so this will be bigger. This y will be bigger than its mean. It's high, so this will be a positive. Again, a negative times a positive contributes another negative. So you're just adding a bunch of negatives when the pattern is going down. Alright, so I hope I've driven this point home. The formula reinforces what we're staring at. Okay, and we've converted the values into standardized numbers, in standard deviations from the mean, and what that effectively does is make R an index. So how do we summarize all that? So facts about R. There's no distinction between explanatory and response variable x or y unless we're specifically instructed to plot one variable versus the other, or you're looking for some sort of relationship where x predicts y. Okay? So, remembering where x is the explanatory and y is the response. And we always plot the y versus x. Okay, so whatever variable is mentioned first, that goes on the vertical axis, and then the other one goes on the horizontal axis. So the fact that if it doesn't matter which direction, which variable is on the horizontal and which is on the vertical, then you're basically saying that one doesn't necessarily cause the other. We don't have the same interpretation as explanatory and response. It's not pushing the relationship. X is not necessarily forcing the relationship. Okay, so when we calculate R, we're just looking at a tendency, an association. It doesn't necessarily mean that one causes the other. The second point is variables must be quantitative. We cannot calculate R for categorical variables, in other words. Number 3, R has no unit of measure. Why is that? Well, let's say we were using, we were computing something that was measured in millimeters. Each time we standardize, we are taking the difference, deviation from the mean, and dividing by the standard error. So we've eliminated, these have millimeter units, that has millimeter units, they cancel. And this is actually giving you standard deviations from the mean. So it is that unit, but it's now in standard deviations from the mean. Okay. But essentially there's no units on it, okay? We're going to interpret it as no units on it, but it is giving us the standard deviations from the mean multiplied by standard deviations from the mean of the variable y. So no units. It's just R. 4. Direction. The direction can be positive, and I say two variables are positively associated when when the above average values of one tend to accompany above average values of the other, and below average values of one a company below average values of the other. The direction is negative, however, when two variables are negatively associated when above average values of one tend to accompany below average values of the other, and vice versa. Okay, so that's exactly what I described. The strength of R is between -1 and 1. The way it's computed forces it into that interval. R of 0 means no relationship, R of 1 means perfectly positive linear relationship, and R of -1 means perfectly negative linear relationship. R only measures the strength and direction of a linear relationship, not a curved or clustered relationship. So R is telling you, in terms of the strength, how close it fits on a line, okay, how close the values fit on a line. So even though your pattern might be close to a line, like we saw a curved relationship could be like this, that's not, the values aren't perfectly on a line, they're perfectly on a curve. So you shouldn't calculate R for that. I'm sorry it's not so smooth. It's hard to do on here. I should actually smooth it out first and then put the dots. Anyway, so number 7. Okay, so everything was just, right until now was a review, okay? Now I want to say, since R consists of the mean and standard deviation, R is also sensitive to extreme values or outliers like the mean and standard deviation. It is critical to consider the validity of outliers and to drop outliers resulting from measurement error. So if you computed if you collected a data point incorrectly through measurement error, so you were measuring items on a scale or computing, you had to do some intermediate computation to get a data point and you did it wrong, that's a measurement error. If you've identified values that really sit apart from the rest of the pattern of the data, investigate them and then drop them. But if you have outliers and there's no good reason to drop them, you shouldn't drop them, okay? So they're not an error, they're not an error of keyboarding, like data entry, not an error of measurement. You have to keep them or make a strong argument why you need to delete them. You should not delete outliers without cause, good reason. So, an outlier is a deviation from the overall pattern and must be reported. A more appropriate definition in the textbook is that an outlier is a highly influential point. So when we turn to scatter plots, we talk about outliers more in the vocabulary of influential point. We use that terminology. It's influential in that it will affect estimation and prediction results, an estimation of the line in this case. Thus, it is important to verify if an outlier is a result of data entry or measurement error. If so, drop it. Otherwise, if it is an actual observation which must reflect a paradigm shift or structural change, it must be included and don't drop it. So, for example, say the pattern of your data was like that. So you collected data here. I won't describe the relationship because we have many examples to look at, but you have collected data there, and then somehow you get some extra funding for your project, and you're able to get another data point, either another interview, or you can buy some proprietary data from a company that stores data, and so you get an extra data point. Now that data point is outside the regular pattern of the data. The pattern would predict that it would be down here, not up here. Like, look, it's way off if we were to estimate a line through here. So what's going to happen is that line, which should have been like that, will now have to fit and capture that point. Because of it, it's going to shift the line from being like this. Well, I'll make it. So it should go through like that. It'll change the line from being like that to fitting close to everything. It's going to have to flatten it to include that point. So it changes the slope of the line, and it changes, so it changes the slope, and it changes the y-intercept as well. Okay. Now I should have probably used my lines here, but okay, I'll try that next. I haven't figured out how to rotate these lines, but okay. All right, so that's what we'll get into that with some exercises as well. Okay, so this was called an influential point because it's going to radically change the relationship. It's going to change the line, making the slope flatter, and changing where it hits the y-intercept. Okay. Another point is, people will say, well, is that really a relationship? So like here it's clearly, it's negative, but sometimes it's like, well, is there really a relationship there? So some of those that I showed you before that were pretty scattered, I'll give you another example. It's really scattered around, but seems to go down, but really, really scattered points. Is this a useful relationship? Is it something that we should count on? Is it something we should use for prediction? Can we say that X explains Y? Can we get Y from X in a line or linear relationship? Well, you could check something like that doing this calculation. This is a rule of thumb that is sometimes used to be able to how can I say, categorize or to comment on your R, to summarize if it's indicating a good relationship. So if you see a sort of a line, you see a line here, it's very scattered around the line. Is there a relationship? Is this enough? Is it just by chance that they're kind of like that, or is it actually downtrending? And the way you can check that is using this rule. So let's say N was 100, you had 100 observations, what would R have to be to demonstrate a linear relationship? Well, plugging it into here, then R would have to be greater than, well, the absolute value. So as a positive or a negative, depends what you get. So I'll just, yeah. Should be greater than 2 divided by square root of 100. I really need more space. Let's do that again. So R should be greater than or equal to 2 over square root of 100, which is 2 over 10 or 0.2. So that seems like a very low number. But in fact, an R for 100 observations, an R of 0.2 or more would indicate a relationship. A linear relationship exists. Okay, as long as you have a graph first to attest to the fact there's a linear relationship, if it's 0.2, you could actually report there is a linear relationship there using that rule. Okay. Lastly, provided the scatter plot and calculation of R reveal a strong linear relationship, we can then use R to estimate the least squares regression line, useful for prediction and estimation purposes. Okay? So I give you an example here. Let's actually calculate R rather than dancing around the issue. Let's actually get it. Now let's first, I want to get the answer by making the scatter plot. Make the scatter plot for these data. Give you 5 minutes. Make the scatter plot for these data and tell me what R is approximately. So these represent the measures in millimeters of insects. So fossils, you know, fossils have carved into them the pattern of bones, right? So inside these fossils, the measure of the leg bone and the arm bone for these insects are provided here. So this is the leg bone, this is the arm bone, and for insects, arms are bigger than legs, you see? However, what we want to do is, so that it's consistently, the arm is bigger than the legs. For these different fossils, we want to say, are they from the same species? So is the relationship or the proportionality between arms and legs the same? It's not exactly a business question, but it's a good, this is just an interesting example. All right. You might want to do this with other, other pairs of data points to see if is there a relationship. Is there a relationship among these pairs of data? So make a plot, and I'll give you 5 minutes. I'm gonna go get some water. I'll be back. All right, I'm back. Did you do it? All right, so I gave you the space to do that in. And what you should see is if I put, so notice here, humerus versus femur. It means that humerus is Y and femur is X. Okay, so femur is here because it's Y versus X. It's always Y versus X. And humerus here. Well, let's make that easier. Let's write leg and arm. Too fancy for me. So leg bone, arm bone. And when you plot them, the leg is between 38 and 74. So you could start, you know, I'm going to put a break in the axis, so I'm going to be off the origin. I'm not going to be at 0, 0 as the origin. On this axis, I'm going to plot, let's say, I could start at 30, and then 40, 50, 60, and 70. And then up here, I want to go between 40 and 84. So I could break it here and start at 40, a little bit smaller, 50, 60, 70, and 80, just to give you an idea. And what you'll see is the data points. And you can use the corner of a piece of paper to help guide you. So for the first one, 38, 41. So 38, I didn't put this down. So this is going to be 30, right? So 38 would be about here. And 41 would be about here. It's about there. And then 56, 63 will be like there, and 59, 70 So 59 is almost 60. So I'm going to go here. 59 and 70 brings me all the way up here. So why am I doing this? Just to get you a feel for this, of what you're staring at. You don't have to do this again, because you could just plot this in software or get your assistant to do it if you had a few values. Okay. And 64, 72. 64 would be about here, and 72 would be up here. And then 74, 84. That's too high, isn't it, for 72? Let me redo that one. That would be more like 64, 72. And then the last one is 74, 84. 74 would be about here, and 84 would be up here. So look at that. They're pretty much, my drawing isn't the greatest. sketch, but that's the idea. Something like that. So you see a few values. I pretty much see a positive trend, linear relationship. What I want to know is, because the direction, first we answer the questions. Is there a linear relationship? Yes. So you can say linear, it's positive, and it's strong. The R is probably positive 1. But now let's calculate it. Are these fossils likely to be from the same species? Yes, because they have the same proportionality between the leg and the arm bone. And what is that proportionality? Basically what you'd be finding to find that would be the slope of this line. But right now I just want to get R first. Since the R is strong, you can see it here, it's very close to 1. Can the length of the arm be predicted from the length of the leg? Yes, it's a good prediction, and it's a good prediction in this range of values. Okay? You don't want to take a statistical prediction line and use it outside the range of values. Okay? So I've chopped up, I started the coordinates higher up than the origin. This line, the statistical line, does not extend down to 0, 0. Mathematically, we could extend the line, but it wouldn't make any good predictions. So what am I talking about predictions? Well, what would we expect at 45? What would we expect the arm bone to be if the leg bone was 45? That's what we want to figure out. So if the arm bone is 45, that would be here. What should be the leg bone? Well, if we find the line, we can get very precise at the value. It looks like it's going to end up being, if there's a line here, it should be about 50 something. That's what we want to do with it. Okay, so let's calculate the R. So the calculation for the formula below, remembering this is the formula. And it's an average of the multiple of the standardized values capturing their tendency, whether they're reinforcing or their opposite effects, and how closely they behave. So we're going to look at this. So we expect X and Y to behave very similarly, right? Because we see it's a positive relationship, and it's a very strong relationship. So let's see, if you take these values and these values and you enter them into your calculator in stat mode. Now again, I don't know which calculator you have, but you should, if you're going to use the BA2 Plus that I recommended, I'm going to provide some instruction for that right now. And I say you can buy that on your iPhone. For $15 or more, a little bit more. So let me give you the instructions, and people who have a different calculator, you can try finding out how you do that. So on the BA2 Plus, you're going to hit second data, I'm just going to put it over here. So you're going to hit second and data, and the spreadsheet opens for you where you can enter values. You hit second, clear work, and what comes on the screen is X01. X01, tell the calculator 38, enter, and go down. Now it asks for Y01. So for Y01, now you enter 41. 41, enter, down. And then we've done one pair, now we go to the next pair. Now it asks for X02. You tell it 56, enter, down. And then Y02 is 63, enter, down. And in this fashion, enter all of the data. Okay, so repeat that for all the values. When you've done that, ask the calculator second stat. And what do you see on your screen? What do you see on your screen? Very good, Yvonne. You see Lynn. Now, scroll through, going down with the arrow. You can get all the data. All the data here, all the results will be in the calculator. N is 5, X bar is 58.2, SX, the standard deviation, is 13.19. Then it tells you sigma X. That is not the sample standard deviation. Sigma X means it's not sigma X. Sigma X is the population. It calculates the population standard deviation, so you don't want that one. Then keep going. Y bar is 66. One more time. Standard deviation of Y is 15.89. And then you ignore sigma y as well, because that's just calculating dividing by a larger number as though one larger, assuming that you're entering population data. So you have to know you don't need that one. If you watch my videos on statistics, standard deviation, you'll see me talk about that. And now it tells you A, it tells you B, and it tells you R. A which I haven't put here, but let me add it. So what is A? A is equal to negative 3.66, and B is equal to 1.2. I need to remove that, don't I? B is equal to 1.2. And finally, R is equal to 0.99. Everything from the calculator. So, even though I'm going to carry out the step-by-step calculations to make my points, you already have the results. Okay? Any questions about that? Now, if you have a different calculator, you can take some time to learn how to use that. If you know how to do this in Excel, you can do it in Excel, but it's using the stat mode in a calculator is probably the fastest way to do this. Maybe not. I don't think I've ever calculated correlation in Excel, but as long as you know how to set up the table and everything, I think it'll do it for you. So let's do it step by step now and confirm our answers. So what we're going to focus on first is calculating R. And then we'll talk about these results. So these are also statistics. R is a statistic estimating the correlation if you had all the fossils. And these are statistics, estimates of the y-intercept and the slope. As a 1.2. All right, let's do this here, entering values instead and going step by step to make a point. So if I was to standardize 38 with the information I got from my calculator, 38 minus the 58.2 is equal to negative 20.2, and now divide by the standard deviation. And you get negative, make it a little bit bigger. You get negative 1.53. Now let's do the one beside it. I don't want to just fill in this table. I want to make some observations. Beside it, we have 41. 41 minus the mean of y equals divided by 15.89, the standard deviation of y. And I get negative 1.57. Do you see? You get, when x is below its mean, this is 1.5 standard deviations below, y is also 1.57 standard deviations below. They're very similar. Okay? So this is going to reinforce the idea that our r is almost exactly 1. We're very close to it. Next one. 56 minus 58.2 divided by 13.19. Did I do that right? 56 minus 58.2 equals divided by 13.19 equals, I did it wrong. So negative 0. I'll make a little comma. 1.6. I'll say 1.7. So if I ever ask you to do this, just do it to as many decimal places as I say, or just use 2 if I don't say. So it's negative 0.17. So it's very close to the mean, right? Because 56 is very close to 58. And the next one, 63 minus 66, which is also close, equals divided by 15.89 is negative 1.9. What am I saying? Negative 0.19. Again, x is close to the mean. It's only 1 standard deviation, 0.17 standard deviations below the mean. Very, very close. At the same time that y is very close to its mean, below by 0.19 standard deviations, okay? So this is going to happen all the way down. So you can fill in the table. I'm doing it at the same time, so I'm pacing myself. So let me know if I make any mistakes, but you should be doing this, okay? So yes, you need to know how to use your calculator and to make the table like this. So this is 0.06. And then this is 0.25. Let me check that again. Or just tell me if it's wrong. I guess I should check it. So this one is not as close as the other ones, but anyway, it's still in the same direction, right? So they're both above the mean and not too far. This one is pretty much at the mean, and this one is a little more, but still small in terms of standard deviations from the mean. So we notice that when one is negative, the other one's negative. But also when one is positive, the other one is positive. So finish this table. And you can do this in Excel as well, faster. Am I getting all the same numbers as you? So again, same direction. This is a little bit greater than the mean, 0.44, and this one's about the same, 0.13. And finally, so again, these reinforce each other. When this one's above by 1.2, this one is above by 1.13. Very similar. Okay, so when we multiply these amounts, we're going to multiply, and they're all going to be positive, right? They all have the same sign. They're all going to be positive and similar. So it's almost like squaring. They're so similar. So 1.53 times 1.57 is 2.41. Well, 40. No comments. You guys are quiet. I hope you're working. And then 0.17 negative times 0.19 negative is 0.03. And then 0.06 times 0.25 equals 0.015. And then 0.44 times 0.38 equals 0.17. And 1.2 times 1.13 equals 1.36. Okay, so they're all positives. Now what do? Now I sum those up. The formula says take those and sum them. So total them and then average them. Again, I mentioned this before, this is like the average. Okay? So you're going to divide by one less. You lose a degree of freedom because you've put an estimate in there. The estimate of the average of the pair. It's like the pair of means, sample means. So when you put all that together, you get 3.98. And then you take 3.98 divided by 4, and you get 0.995. Okay, let's see. I want to see my results again. My R in my calculator was 0.994, so it's just a rounding. They don't, like, obviously the calculator doesn't round like I do. The calculator gets 0.994. My result ends up being 0.995. They're pretty similar if you round to 3 decimal places. Sorry, I'm back. You didn't hear that. We got the R. I've done it once. You should be able to replicate this process and understanding what the formula gives you, what it's doing. The way that you receive the table this time was with the standardized values. But this took quite a while, right? Because you're doing x minus x bar equals divide by standard deviation. It's like a lot of keystrokes to get each and every one. It's a faster way to do this with the tables, but the reason I did it this way was to illustrate to you what's happening in terms of standardized values. You can really see what's going on and what this formula achieves. So the other way is just to take the deviations from the mean and multiply those, and then later divide by, because we keep on doing this, we're doing it across the board. Why don't we just do it at the end? So you can do that. So that generates a separate formula where this is R. This is also R. So I don't have to standardize each one. That's a constant. That can be put out here. So I can just do a multiplication of the deviations from the mean and then sum them up and later divide by the n minus 1 and standardize the values. So this is the same formula as this one. So what is it? What is this here? If I take this together with this, you should recognize that looks familiar. If you did watch my video on all the other videos and on the standard deviation, you know that the standard deviation is equal to the square root. Actually, let me say the variance. I don't even know why I'm using that symbol. Okay. The variance is before I take the square root. And it would be, the sample variance would be calculated like this. So if you watched my video, you saw that the variance, the sample variance, is the square deviation from the mean. The average of the square deviations from the mean. So I could write it like this, which looks a lot like now in blue I have the variance. This is the variance, sample variance. In red, the only thing that's different is I'm looking at how the deviations of X from its mean relate to the deviations of Y from its mean. Okay, so by doing this, I'm going to get a sign out of this that's going to tell me about the trend, if it's positive or negative, just like we did with, just like we were looking at with the correlation. So this is called covariance, where this is sample variance, this is called sample covariance. And the symbol that we use, well, actually I just use words for this. So this is called covariance. X, Y. Okay? And I'm going to call it the sample covariance. So in fact, that is right here. So really, R is the covariance standardized. That's what R is. It's the standardized covariance, whereas covariance gives you the sign of the relationship between the variables, or the direction tells you the sign, the sign tells you the direction of the relationship. If it's a negative, it's a negative trend. If it's a positive, it's a positive trend. By standardizing, you're going to get R as an index, and you're going to get it on a scale that's from -1 to +1. The sign does not come from these because standard deviations are always positive numbers. The sign is going to come from the covariance. All right? So R and covariance will have the same sign, though they'll have different values. R is always between -1 and 1, and we know how to interpret it. Any questions? Notice, even though I would take, for this variance, I take the square root to get the sample standard deviation, I don't take a square root here of the covariance. There's no square root of the covariance. So because of that, we don't put units on covariance. We just put the number. And that's why we're happy to get rid of the units completely by standardizing it, because really the units don't make sense. Just like the squared values here don't make sense. That's why we'd have to take the square root to get the standard deviation. All right, you have to watch all the videos to understand what I'm talking about. I hope you're up to date. Okay, next problem. What you can do, is you can go through the table and prove to yourself you'll get the same answer using this other version of the formula. So here you have example 4 for nonlinear association. Make a scatter plot of mileage per gallon versus speed. Here's the data. And if you plot it, you're going to get this sort of thing. I think it looks like that, which is a curve. And we already know from here, you guys should do it, but this is a non-linear relationship. It's actually a curved relationship. You shouldn't calculate R, but if you did, the R would be close to 0 for the reasons I explained before. Okay. And make all the calculations here so you can practice that. All right, so now that we've done this, and I actually made a video about this already, to review lines. If you need to learn more about lines or remember how lines work, computing the equation of the line, and make a video on computing the equation of the line for y equals a plus bx. So watch that video. I'm not going to do that again here. Oh, my picture is all messed up. Okay, and I also have a video about this slide 7 or page 7. I hope if your notes are all messed up, let me know so I can give you the right ones. I can fix this. There's a video on this as well. This is going to help you create the prediction line. It explains what's going on here, and the video will be better than me repeating it. And you know what? I'm going to leave you guys to do that. I think I'm going to leave you to watch those 2 videos. I don't know, I think you need to read the rest. So this, so 10, 11, so what did I say, 13? Okay, what I'm going to say, I'm going to tell you not to worry about 10, 11, and 12 either. Okay, don't worry about pages 12, 10, 11, and 12 either. That's going to be for next semester. Well, you can read them. Okay, but I'm going to skip them for now. So what I'm going to do is just talk about the last few things. What you can do if you don't follow what I'm saying is just watch those 2 videos and then pick up here. So what I've done is calculated the prediction line. The prediction line is the result of the minimization of the sum of the squared residuals. that you'll see in the video I explain. The result is a line, but because it's a statistical line representing observations, it's not the mathematical line. We have to give it a different name. So rather than saying the line is defined by y equals a plus bx, we say y hat is equal to a plus bx. I could even write okay, y hat equals a hat plus b hat x. But I don't do that. It's too messy. But those are estimates. A and B are estimates intended to estimate the actual line if I had all the data. And anyway, there's more to say about that, but I'm going to skip that. I just skipped that so we don't talk about that. But that's why I'm just going to write it like this, so I won't get into that. All right, so what are the properties? Because this line fits closest to all the points, and the value in the data set for x and the data set for y, the value that is closest to all the points in both directions is the mean. And I refer you back to my discussion video on mean to know what that's about. So mean is the center of gravity. It's closest to all the other values of x. And the mean of y, similarly, is closest to all the values of y. It's the center of gravity, and because of that, x bar, y bar has to be on the line because that is closest to all the points in both directions. All right? So x bar, y bar is a point that falls on the line. To make a line, all we need is a point and a slope. The slope is calculated like this. Now this formula comes out of calculus results. When you minimize, you optimize, those are a result of you conduct calculus with the systems of equations that comes from all the values. And I'm not going to say anything about that because this course is an introduction, but this is the result. Okay, now this result, you're going to be able to see all these formula, but you can remember it nicely with the mnemonic risk, R sy over sx. Because in finance, actually, B, the slope, represents the sensitivity of the values of y with respect to x. So I'm going to give you an example of that. Well, actually, I gave you notes on that, and I highly recommend you review them. So we have a point, we have a slope. When you have a point and a slope, you can calculate the equation of a line. And putting everything into the equation of a line, the point and the slope, you can solve for the intercept and conclude with the line up here. So you can practice these steps. The least squares prediction line for the fossil data, for instance, these are the means that you remember. The slope was 1.2 we got out of our calculator. That's calculated as R sy over sx. And the intercept you get by plugging everything in, the point and the slope to find A. And then we conclude this is the, doing it that way, this is my line. Now remember, in our calculator, we got A of 3.65. So the numbers are slightly different because it's probably because the rounding, okay, just because of the rounding. So in our calculator we got y hat equals negative 3.67 plus 1.2x. So it's a little different, but not too different. And that's just because of the effect of rounding, making these tables. And that's it. That is the prediction line. Now, what do we do with this prediction line? So in these notes, I go through and I answer. If you start noticing, I keep on having the cues, right? Those are the questions that I'm expecting you to answer. And I just show you an example, a set of examples. So question 5 would be, so one of the kinds of questions I can ask you, interpret the slope and the y-intercept of the prediction line. Question 6, use the prediction line to predict the arm bone when the leg bone is given. Question 7, what is the residual value? Question 8, are any observations influential or outliers? And question 9 is the last kind of question I'm going to ask you. What proportion of variation of y is explained by x? This is called the R-square. It's known as the coefficient of determination. When you square r, you just take r to the power of 2. You have a new interpretation. R is now a percentage, and it represents the proportion of the variation of the dependent variable, or the the response variable y, that is explained by the explanatory variable x. So you obviously want that to be high. You want to say x does a good job of predicting y, so that it can be used so that the line can be comfortably used to make predictions. Okay? So what I'm going to do is leave you guys with this. Watch those other videos in between that I mentioned, and work through the notes. Let me know if you have any questions. You get to skip all of these notes here. And then you get to the exercises on page 19. So you can start reviewing these exercises on page 19. Now this is the only one I don't have an answer for, an answer key for. Maybe I'll do these and then we'll go. The rest has solutions and videos and things. So explain in each case what is wrong with each statement. There is an R of 0.6 between gender of a student and scores on a statistics exam. What's wrong with that statement? What's wrong with that statement? Nobody? Well, R should only be computed between two quantitative variables that have a linear relationship. These are not both quantitative. Score on a stats exam is quantitative, but gender of students is not quantitative. So that's the problem. Gender is a categorical variable. Okay. The number that I assign to gender, if I make female a 1 and male a 2, for instance, somebody else might have numbered them differently. That's perfectly fine. Okay, so the number assigned, the value doesn't, like, it doesn't, to use that to make calculations wouldn't mean anything. Averages wouldn't mean anything. You'd have to use different kinds of statistics for that. Not averages, not standard deviations, and definitely not R. Okay, because it uses both. Okay, next one. R is 0.23 bushels, R is 1.09 between student scores on a math exam and a statistics exam. What's wrong with that? Now they're both quantitative, math exam and stats exam scores. But what's wrong with 1.09? Right, so there's something wrong because R cannot be more than 1. So that's too big. Okay? This symbol means in. So that's why that one fails. What about the next one? R of 0.23 bushels was the correlation between the amount of fertilizer and yield of corn. Well, yield is numerical, quantitative, and amount of fertilizer is quantitative. And R is between -1 and 1. What's wrong with the statement? The problem is R has no units. It can't be bushels because R doesn't have a unit. Okay, so that's the problem. No units. Or R is an index. It doesn't have units. Finally, since R is equal to 0.89 between cups of milk consumed per week and height, we know that drinking milk makes you grow. What's wrong with that statement? The problem is association does not imply causation. You can't say this makes that happen. You'd have to have an experiment. You'd have to have more evidence than just looking at an R. Right? Right. There can be other reasons that drinking milk makes you grow. Not necessarily. Sorry, there can be other reasons that make you grow, not just drinking milk. It's not like drinking milk is going to cause you to grow. There could be limitations by your genetics. It could be other things, other variables. So we're not saying milk makes you grow. We'd have to look into that. It just looks like people who drink milk are taller. Maybe milk is part of the story, but not the whole story. Okay? Also, there's limitations. If you drink a ton of milk, you know, there's a threshold where it's not going to contribute much. And even though a pattern works in a certain range, doesn't mean that you can extrapolate outside of that range to make predictions. That's explained in the notes. That discussion about calculating outside of the range of data is done early on. So I encourage you to take a break. When you're fresh, read through these notes and let me know if you have any questions, okay? Do you have any questions right now? So today is Thursday. I'm going to post questions on Sunday, we decided, right? So I will post questions on Sunday, and they will just be with regression and probability. Watch all the videos you can on those topics. I have, in terms of regression, the videos are before the probability, in amongst the review questions that I did for the exam. Then there's the scatter plot videos I mentioned you should see, and the regression ones. Anyway, there's videos on RLS that you should watch. Let me see if I can put all the video numbers in that chat. I'm just looking for my playlist. Okay, so right. So I have videos 48, V48, V49, V50. Okay, that's going to cover this. And then 49 and 50 covers this material. Okay, in the playlist. Yes, I'll send you those grades. I'll send you those grades by email. All right? So you know how you've done. Let me know if you have any problems with your notes, like this set got distorted. Any other questions? Otherwise, I'm going to say goodnight. So just text me if you need anything. If you need more direction on maneuvering through the videos or the material, there's lots of material. Just need to organize yourselves. I know it's a tight schedule. I really wanted to do this in Verano Largo, but they insisted we do it now. The test will be on Sunday again, yes. The test will be on Unit 3 and 4. Ah, that's right, since it's Father's Day. Well, I can give it to you on Sunday, and you can give it to me on Monday. How's that? Anything else? Keep studying. Study steadily, okay? Keep studying. Everything is there, really. And if you find conflict, let me know. Yeah, I'm going to send it on Sunday and it can be due Monday. I think we changed the dates to Sunday. We agreed to change the dates to Sunday. You want it on Saturday? You want the test on Saturday to Sunday or Sunday to Monday? Sunday to Monday? Okay. Yeah, not Saturdays. Keep studying because you need, Friday, Saturday. Saturday is a good study day. So you can get through the videos and make sense of things and you're not shocked when you see the test. All right? Anything else? Okay. So I'll post on Sunday at noon. So then you can just look at it and brainstorm. And then it'll be due on Monday at 9 p.m. And then you need to start Unit 5 and Unit 6. And again, all the videos are there. I won't meet with you on Tuesday next week, but you guys have all the videos. Email me if you need anything, and we'll meet on Thursday night. So I'm going to meet with you 1 week from now, but you have my voice, you have my demonstrations from here on out. Lots of exercises. Just make sure you set aside the time and cover it all. Okay? With the tests, make sure you work independently, all right? You have so many materials, you shouldn't have a problem. If you want to compare answers, I get it, but don't copy, because I can tell when you copy. It's painful to watch. All right, that's my plea for today. Okay, it's 8:50. I'm gonna say good night, and keep in touch. Okay, you can text me. You have my number if you need something, if you're confused about something. Take care, be safe, and we'll be on live stream next Thursday. Otherwise, you know how to reach me. Good night.